Okay, good morning all. Now today I am going to start with the topic Laplace transform of unit step function. So in the last class we have discussed with the Laplace transform of periodic function. So I hope you have understood the topic and you have gone through the assignments. So today's new topic will be how to find the Laplace transform of a unit step function. Now before I go into how to find the Laplace transform of a unit step function, I must say what is a unit step function. Now as the name says, unit step. So how we define it? First let's see what is the definition of a unit step function. Now the unit step function, which is normally denoted by the symbol ut minus a, is defined as ut minus a will be equal to 0 for t less than a and will be equal to 1 for t greater than equal to a. So the word unit means that the value of ut minus a for t greater than equal to a will be 1. 1 stands for unity, so that's why the name called unit step function. And the value of a should be greater than or equal to 0. So now it may happen that a is equal to 0. If a becomes 0, as a particular case, we get the unit step function to be something like this. That is, you put a equal to 0 in the previous definition. So you will be getting ut equal to 0 for t less than 0 and will be equal to 1 for t greater than equal to 0. Now let's see what is the graph of this unit step function. That is very, very important. From there we can tell you that why it is called a step function. Now if you look at the graph of this function which I have drawn here, it is very simple to draw, because you see ut minus a will be 1 for t greater than equal to a and it will be 0 for t less than a. So we have drawn two axes, the x-axis and the y-axis. On the x-axis we have taken the time variable t, and on the y-axis we have taken the function ut minus a, right? You see over here. And we have taken an arbitrary point a on the x-axis, right over here, right? This is a, and a is definitely positive. So you can see that when the value of ut minus a will be 0, that is on this x-axis, when t is less than a. So it forms a straight line here from 0 to a. I mean, it extends from minus infinity to a. And then when it is greater than or equal to a, the value is 1. ut minus a is 1. So we have taken 1 here on the y-axis, which is the function value, and it is basically a straight line because it's a linear function. So straight line parallel to x-axis, right? So it's a constant function. So ut minus a becomes equal to 1 for t greater than equal to a, and that extends right over there. So you can see from the nature of the function that I've drawn over here, it is a step function because there are steps formed. This is one step and there's another step. It looks like a step. Since it looks like a step, it's called a step function, the function being discontinuous at the point a. So, and since magnitude of this step, which is called the height or magnitude here, okay, is being 1, so it is sometimes called unit step function. So that's a concept of a unit step function. Now let's find out that how to calculate the Laplace transform of a unit step function. Yes, before we go into that, we just define in a more general way. If we consider the product, that is ft multiplied by ut minus a, ft being any function of t continuous for t greater than equal to 0. So ft into ut minus a will be 0 for t less than a and will obviously be equal to ft for t greater than equal to a. So if we take the product of ft with ut minus a, it's very easy to see that this function will be something like this. So it will be 0 for t less than a and ft for t greater than equal to a, being a positive quantity over here. So what happens is that, then what is the significance of this function? The function that we have defined right now over here by taking the product of ft with ut minus a represents actually the graph of the function ft, which is shifted through a distance a. It is shifted through a distance a. Okay, on the right. So that is the basic idea of ft ut minus a, which we have defined it over here. So it is basically represents the graph of the function ft, whatever the function is, which will be shifted through a distance a to the right. Okay, so this is very important. This concept we must be clear with it, because we'll be doing some problems based on this concept. Now let's come to find out what is the Laplace transform of a unit step function, which we have defined in the previous article. So to find the Laplace transform of a unit step function, we use the basic definition, like we have been doing it for so many proofs. So we apply the definition of the Laplace transform on the unit step function ut minus a, and we get integral 0 to infinity e to the power minus st ut minus a dt. So we integrate. So what we do is that we just break it into two integrals, 0 to a and then a to infinity. As we know that for t less than a, ut minus a is 0. So it is e to the power minus st into 0 dt. And from t greater than equal to a, it is 1 unity. So in place of ut minus a, I'll put 1. So I'll get integral a to infinity. The second integral becomes e to the power minus st into 1 dt. So it's a very simple integration. The first integral becomes 0 because the integrand becomes 0 in that case. And if you integrate the exponential function e to the power minus st, you get e to the power minus st by minus s. Limits are put from a to infinity. And s is a positive quantity here. S is assumed to be positive. If s is positive, as we are considering here, e to the power minus st will definitely converge, because as t tends to infinity, e to the power minus st will be tending towards 0. So the upper limit is 0, assuming that s is positive, and the lower limit is, you put the value in place of ta, we get e to the power minus s by s with the minus sign. One minus sign will come from the fundamental theorem, thereby making it plus. So eventually the result is 1 by s into e to the power minus s. So the Laplace transform of a unit step function ut minus a, being a positive quantity, is 1 by s into e to the power minus s, right? Where s is obviously a positive, greater than 0, because if s is not positive, then this integral will divert, because it's improper integral of first kind. So if s is negative, less than 0, so we find that it is e to the power some positive quantity multiplied by t, and therefore as t tends to infinity, it will definitely go to infinity, because we know an exponential function is strictly increasing, so it will tend to infinity, and therefore we won't be able to find its convergence. So s must be positive for convergence. So as a particular case, as I was telling you, that a can be 0. So if a is 0, then you just put a equal to 0 in the basic result that we have just now got, and you should get L of ut to be equal to 1 by s, because e to the power minus s will be actually equal to 1, and so you get 1 by s. So L of ut becomes 1 by s as a particular case. Okay. So that is where we find out the Laplace transform of a unit step function. Now I come to two very important, in fact three, and the third one will be the generalization of the first two theorems. I come to two very important theorems on this particular article which I am discussing on unit step function. That is, you see, if you have a function ft discontinuous at a, and let's say ft is defined to be equal to f1t for t less than a and f2t for t greater than a, then you can always express this very function ft in the form of a unit step function, and the result says that this is the result. That is, you can write ft as equal to f1t plus f2t minus f1t into multiplied by ut minus a. So that means you can, or you are able to represent this function ft in terms of the unit step function. Now how we can do that? There must be a proof behind it. So I'll go to the proof. It's a very simple proof though, but I'm going to it. Now from the definition of unit step function, which we have just now discussed, okay, we can write, because we just discussed the concept of that product function ft into ut minus c, we just remember. So if we use that concept over here, ft, okay, can be written as f1t plus f2 minus f1t into 0, because my target is to prove that ft is equal to f1t plus f2t minus f1t into ut minus a. So I write ft equal to f1t plus f2t minus f1t into 0 for t less than a, and for t greater than a, it will be f1t plus f2t minus f1t into 1. Okay, for t greater than a, because the ut minus a is 0 for t less than a, and ut minus a is 1 for t greater than a. So that's why it is so. So if you put the values of 0 and 1 and calculate, you see that you get ft to be equal to f1t for t less than a, and you get to be equal to ft to be equal to f2t for t greater than a. Okay. So what we can say that this very function ft, which we write as f1t for t less than a and f2t for t greater than a, can easily be written in the form of a unit step function as f1t plus f2 minus f1t into u t minus a. So this we can do. We can do that for any such types of functions. Now this result is not restricted to two functions here. It may be extended to for any number of such functions. So let's come to the next theorem, that is theorem 3, which is the next theorem. I'm not numbered the theorem though, which is actually a more generalization of the previous case. Instead of considering two functions by breaking into two subintervals, we now consider three subintervals. And let's say the function is now defined in this manner, that ft equal to f1t for t less than a1, ft is equal to f2t for t lying in between a1 and a2, and ft is equal to f3t for t greater than a2, right? Now this function can be expressed as ft equal to f1t plus f2t minus f1t into ut a minus t minus a1 plus f3t minus f2t into ut a minus 2, where of course ut a minus 1 and ut a minus 2 are unit step functions. I'm not going into the proof of this this theorem in particular, though I have given the proof of the previous theorem. I'm excluding the proof at this level. So I think you have understood that for three subintervals, if we have this cases, points of discontinuity being 2 here. In that case, how to express that function in the form of a unit step function. So in that case, the function ft will be f1t plus f2t minus f1t into ut a minus 1 plus f3t minus f2t into ut a minus 2, where ut a minus 1 and ut a minus 2 are both unit step functions. Now comes a more generalization. In fact, the generalization of the above two theorems, if I generalize it for any number of subintervals having let's say n minus 1 points of discontinuities, if the function has. So let's say if you define the function in this manner, let's say we have the function ft equal to f1t for t less than a1, f2t for t lying between a1 and a2, f3t for t lying between an a2 and a3, and like that fnt for t greater than an minus 1. Okay, so so something like that. So the previous one will be fn minus 1t for t lying between an minus 1 and an minus 2. Okay, so when we have n minus 1 points of discontinuity in the function, then still also this function can be represented in the form of a unit step function. How we do it? In a very similar manner that we have discussed the previous two theorem. If you just generalize the previous two theorem, you'll be able to understand how we can write the general case of this function being able to represent it in the form of a unit step function. So that's what we have done here over here. We can write this function, very function ft, we can be expressed as ft equal to f1t plus f2t minus f1t into uta minus 1 plus f3t minus f2t into uta minus 2, and in this way it continues, okay, till the last term is reached, that is fnt minus fn minus 1t into uta t minus an minus 1. Again you see this functions uta minus 1, uta minus 2 dot up to utan minus 1 are all unit step functions. So any functions like this or function of t can always be expressed in the form of a unit step function. Okay, and this is the way we do it. So it's very, very important. I hope you have understood. First I have shown you for 1 point of discontinuity, then 2 points of discontinuity, then 3 points, then n minus 1 points of discontinuity, having n number of points by which you divide the interval, right? Okay, so this is very, very important. Now we come to another very, very important theorem of Laplace transform. This is called second shifting theorem of Laplace transform. If you remember, while teaching in class, I have discussed the first shifting theorem of Laplace transform. Now today I'll be discussing the second shifting theorem. I told you that I'll be teaching the second shifting theorem later on. So now I am going to teach this particular topic of second shifting theorem of Laplace transform. Now what is the second shifting theorem of Laplace transform? You see on the board is written, if Laplace transform of ft is known to be equal to f bar s, then the Laplace transform of ft minus a into ut minus a, where ut minus a is obviously the unit step function, will always be equal to e to the power minus s into f bar s. Now how it is so? Why it is so? Why L of ft minus a into ut minus a will be equal to e to the power minus s into f bar s? So we can go to the proof. The proof is very, very easy. Again, we start from the definition of Laplace transform like we were doing in all the previous cases. So if we apply the definition of Laplace transform on this function ft minus a ut minus a, so we should get this integral, that is integral 0 to infinity e to the power minus st ft minus a into ut minus a dt, right? Now this can be broken up into two integrals. One we can write from 0 to a, the other one being a to infinity. But you see, from 0 to a, ft minus a ut minus a is actually 0. So therefore the integral being 0, so the integral vanishes. So the previous integral 0 to infinity becomes equal to integral a to infinity e to the power minus st ft minus a dt, because ut minus a is 1. Ut minus a, if you remember, is equal to 1 for t greater than equal to a. So in the range from a to infinity, ut minus a is 1, in the previous case it was 0, that's why the first integral became 0. So let's call this number 1. Now because we have to make a substitution now. So what we do is that we put u equal to t minus a. We put u equal to t minus a, take the derivative on both sides, we get du equal to dt, and now we find the limits of u. When t equal to a, you can see clearly u is 0, and when t equal to infinity, u is also equal to infinity. So making those substitutions, the integral 1 which we written earlier now becomes L of ft minus a ut minus a becomes equal to integral 0 to infinity. In place of t we are putting u plus a, and in place of t minus a we are putting u. That's what we have done. So this becomes fu. So e to the power minus s u plus a into fu du, right? Now e to the power minus s is a constant, so we take that outside the integral, and we are left with integral 0 to infinity e to the power minus su into fu du, right? Now what is this integral 0 to infinity e to the power minus su fu du? So it is nothing but f bar s, because this is Laplace transform of fu, which is actually equal to f bar s, which we have already assumed that it is true. Unless Laplace transform of ft is known to be equal to f bar s, we cannot prove this. So in this whole integral 0 to infinity e to the power minus us into fu du becomes equal to f bar s, and thereby we get the proof of this very important second shifting theorem, which turns out to be e to the power minus s into f bar s. So this is a very important theorem of Laplace transform. L of f t minus a into u t minus a is always equal to e to the power minus s into f bar s, provided you know Laplace transform of the function f t to be known to be equal to f bar s. Otherwise, this theorem will not be applicable. Now, if you use in the reverse manner, that means the first corollary is that corollary number 1 of the second shifting theorem of Laplace transform is, if you take the inverse Laplace transform of the result that we have got, we would get another very important result, which is very often used in finding out the inverse Laplace transform of a function of s. How we use it? Very simple. You take inverse Laplace transform, you will get L inverse of e to the power minus s into f bar s to be equal to the function ft minus a into ut minus a. That means ft minus a into ut minus a is nothing but L inverse of e to the power minus s into f bar s. So this is quite often applicable in solving problems which I was just now telling of inverse Laplace transform, where you get this particular form. If you get this particular form where we know the Laplace transform, the inverse Laplace transform of f bar s, and f bar s is multiplied by a negative exponential function, then you can apply this theorem and find out the inverse Laplace transform of this function, which will be a function of t in this particular form. Okay, so that you can do. Now, as a particular case, if you put a equal to 0, because a can be 0, if you put a equal to 0, the second shifting theorem becomes something like this. That is, it becomes L of ft into ut, and that turns out to be equal to f bar s, and f bar s is nothing but L of ft. Okay, so we get L of ft basically, and you should get that because ut is actually equal to 1, so L of ft into ut should be equal to L of ft. So it is absolutely true. Now comes another very important corollary, actually, coming from the second shifting theorem only. That is, instead, so since we have just now found the second shifting theorem result, if you look at this corollary very carefully, I just state here that Laplace transform of ft into ut minus a will actually be equal to e to the power minus s into Laplace transform of ft plus a. Okay, so this is coming from as a extension of the statement of the second shifting theorem. So this is a very important result, and this result, I'm not going into the proof of this because proof is excluded at this level, but you must remember all these three corollaries. L of ft into ut minus a can be represented as e to the power minus s into L of ft plus a. Okay, so these three corollaries are very important as far as the second shifting theorem is concerned. Okay, now let's come to some illustrative examples of today's class. We have done three things in this class. We have first defined what is a unit step function. Then we have found out the Laplace transform of unit step function. Then we have defined that how a function can be represented having points of discontinuities in the form of a unit step function. And then we discussed the most important property of Laplace transform, the second shifting theorem, and stated the three very important corollaries based on that. Now let's come to the first example in today's class. This example I've taken. The question says, using unit step function, find the Laplace transform of this function. That is, the function is given as ft equal to sin t, t is from 0 to pi, sin 2t, pi to 2 pi, sin 3t, t greater than or equal to 2 pi. So there are 2 points of discontinuity, pi and 2 pi. So accordingly, you have to first find the Laplace transform by representing this function as a unit step function and nothing by any other way. If you do it by any other way, you may get answer right, but you will not get any marks for that. So keep that in mind, because the question says, if I just go back to the question once again, you see, using unit step function, you see over there, using unit step function, you have to find the Laplace transform of this function. So that is very, very important, that you need to follow the instructions given in the problem. So how do I represent this function as a unit step function? That's the question. Very easy, because just now I told you how to represent any function. If you look at the second theorem which I taught today, which was there were 2 points of discontinuities, and basically it's application of this. So you just apply that second theorem over here, and you'll be easily able to write ft as a unit step function. So we apply that, and so I've written here using theorem. We have, so I'm using that theorem. You should state the theorem whenever you're writing this answer in a particular exam. Okay, it's always good to mention the theorems and properties which you're using it over here. So if you use that theorem, we can write ft as equal to sine t plus sine 2t minus sine t. You see, I wrote over there f2t minus f1t, right, into ut minus a1. It was a1 over there, so it's pi. So here in this case is pi, so ut minus pi. Then plus it will be f3t minus f2t. That f3t is sine 3t here, f2t is sine 2t here. So sine 3t minus sine 2t into ut minus a2. a2 here is 2 pi. So ut minus 2 pi. And f1t is sine t, which I have written earlier. f1t plus this one, the first term. So this is the representation, whole representation of this very function in terms of the unit step function, which is a requirement here in this particular problem. We are presenting this in the form of a unit step function before we go into find its Laplace transform. Okay. So what are these ut minus pi and ut minus 2 pi? They are of course unit step functions. So we write that where ut minus pi and ut minus 2 pi are unit step functions, right? Now we know two important things. Just now I told you, if you remember the corollary number 3 in the second shifting theorem, there I told you the Laplace transform of gt into ut minus a will be e to the power minus s into L gt plus a. So we'll use this result, and we'll also use the result that we know, that is L of sine bt. You know the Laplace transform of sine function, it is b by a square plus b square. So all of you know that. So keeping this two result in mind, now what I'm going to do is that I'm going to just take the Laplace transform of the unit step function that I have written in the previous line. So I just blindly take the Laplace transform on both sides. So by using the linearity property, it will be something like this. You see, it's over here. You'll get L of ft equal to L of sine t plus L of sine 2t minus sine t into ut minus pi plus L of sine 3t minus sine 2t into ut minus 2 pi, right? So we'll get this. Now you do one by one. So first step is L of sine t. L of sine t we all know 1 by s square plus 1, because very well known b is 1, so 1 by s square plus 1. Now then what is L of sine 2t minus sine t into ut minus pi? If we apply that corollary number 3 of the second shifting theorem, so we should get, because ut minus pi, right? So your a is pi here, so it will be e to the power minus pi s into Laplace transform of g t plus pi. So g t plus gt is sine 2t minus sine t, so it will be sine 2 t plus pi minus sine t plus pi, right? We are just applying the property. So we get this. Similarly, the third term will be in a very similar manner. Now what is a here? A is here 2 pi. This is here 2 pi. A is 2 pi. So if a is 2 pi, we get e to the power minus 2 pi s right over here into L of g t plus 2 pi. Now what is the gt? gt is sine 3t minus sine 2t. So I write sine of 3 t plus 2 pi minus sine of 2 t plus 2 pi. So we have just applied the property corollary number 3, very important corollary I told you. So we can write like that. So now we have to just simplify. So the first term was 1 by s square plus 1, we keep it like this. Then we got e to the power minus pi s, and then we have got Laplace transform of sine 2t plus pi. So it is sine 2t plus 2 pi, which is L of sine 2t. and minus sine t plus pi, which is minus sine t, so it becomes plus sine t, and if you take the Laplace transform using linearity property, it is L of sine t. So e to the power minus pi s multiplied by L of sine 2t plus L of sine t finally. And then we go to the third term. So in the third term, what we get? In the third term, we get e to the power minus twice pi s. Earlier we got L of sine 3t plus 6 pi. So sine of 6 pi plus 3t is sine of 3t. So it is L of sine 3t. And here you get sine of 4 pi plus 2t, which is sine of 2t. So the minus sign remains as it is, so it is minus of L sine 2t using the linearity property. Now we apply the basic result of L of sine bt, which we wrote earlier. So L of sine 2t is 2 by s square plus 2 square. L of sine t is 1 by s square plus 1. And plus e to the power minus twice pi s, the third term, it is 3 by s square plus 9 minus 2 by s square plus 4. So that gives the result of this particular problem. This is the Laplace transform of that very function. So this is a way we can find the Laplace transform of a function, a discontinuous function having 2 points of discontinuities, by representing that in the form of a unit step function, not by from the definition. Okay, so such types of questions will be very common actually in semester exams, that I give you a function and ask you to find out Laplace transform of the function by first converting that function into a unit step function. Now coming to the next example of our discussion today, it's very straightforward and simple one, but still I will go by it, because this is another type of question you might get from the second shifting theorem. It says that find the Laplace transform of sine t into ut minus pi. It's as simple as that. Find the Laplace transform of sine t into ut minus pi. Now how do I do that? What we are going to do that we're going to use the second shifting property result. But how? Because in second shifting property it has been mentioned clearly that L of ft minus a into ut minus a is e to the power minus s into f bar s. But we are not getting that exact form. It is not sin t minus pi. Had it been sin t minus pi, ut minus pi, I would have applied that result immediately and got the result. But what we can do is that we can represent sin t in the form of t minus pi. Very easily we can do that. How we can do that? This is the way we can do that. We can write sin t as sine of t minus pi plus pi, and sine pi plus theta is minus sine theta. Okay? Because it falls in the third quadrant where sine is negative. So it's minus sine t minus pi. Eventually, sine of t minus pi plus pi, you will consider t minus pi as theta, so it's sine pi plus theta, which is minus sine theta. So it's minus sine t minus pi. So once that is obtained, so I can write sine t as minus sine t minus pi. Now let's make a comparison. I compare, in place of sine t, I'm writing now minus sine t minus pi. There's no harm in doing it. Multiplied by the unit step function ut minus pi with the result that we know ft minus a into ut minus a. So if we compare minus sine t minus pi, ut minus pi with the result ft minus a, ut minus a, what do you get? You get a equal to pi. A is pi, no doubt about that. And ft is minus sine t. It's not sine t, it's minus sine, because there's a minus sign. You see, there's a minus sign over here. So it's minus sine t. So therefore, what is f bar s? Very simple. It's L of ft. And L of ft is minus 1 by s square plus 1, because all of you know what is L of sine t. L of sine t is 1 by s square plus 1. So it's minus of 1 by s square plus 1. So therefore, if you use the second shifting theorem, we'll get the result directly. So what I was asked to find out, L of sine t into ut minus pi, which eventually becomes L of minus sine t minus pi, ut minus pi. Okay, and that becomes e to the power minus pi s into f bar s. Okay, so that is eventually becoming e to the power minus pi s by s square plus 1 with the minus sign. That minus sign will come from here, and that is the answer of this particular problem, and it is direct application of the second shifting property. So we'll get problems like this also, where you have to find the Laplace transform of this function, where you have to use the second shifting property. The function may not be exactly in the form of ft minus a into ut minus a, but you have to represent that ft part in the form of ft minus a, and then you have to solve it. So this is another type of question that I have discussed today. Okay, I hope you have understood. Now coming to the third example of today's discussion is find the inverse Laplace transform of s e to the power minus s by s square minus omega square, where a is given to be positive. Okay, so to find the inverse Laplace transform. Now if you look at this problem very carefully and corollary number 1 of the second shifting theorem. In the second shifting theorem, first corollary, if you go back, you see that I have used the second shifting theorem result in the inverse manner. That is, I told that L inverse of e to the power minus s into f bar s is equal to ft minus a into ut minus a. So isn't this particular problem of the same form? It is asked to find L inverse of e to the power minus s into s by s square minus omega square. Now you very well know what is L inverse of s by s square minus omega square. I think all of you know that. It is what? Cos hyperbolic omega t. So immediately I write that. So I assume let f bar s is s by s square minus omega square, and I find what is the inverse Laplace transform of that, which you all know. It is cos hyperbolic omega t, right? So ft is known to me. When once ft is known, then things become pretty easy. So therefore, I now try to find out what is asked in the question. L inverse of s e to the power minus s by s square minus omega square. So this will be equal to, by definition, will be L inverse of e to the power minus s into f bar s. Now f bar s is already being mentioned as s by s square minus omega square, whose inverse Laplace transform is also known to be ft, that is cos hyperbolic omega t. So we know L inverse of e to the power minus s into f bar s is known to be equal to, from the corollary 1, ft minus a into ut minus a. So since ft is obtained, so ft was cos hyperbolic omega t. So this result will be cos hyperbolic omega t minus a multiplied by ut minus a. And so that's the answer. So the inverse Laplace transform of e to the power minus s into s by s square minus omega square is cos hyperbolic omega t minus a into ut minus a. So it's very easy, but this time the problem we have used using the corollary 1. So corollary 1 is useful in these types of problems where you are asked to find out the inverse Laplace transform, where you see that the function can be written in the form of e to the power minus s multiplied by any function of s, and that function of s whose inverse Laplace transform is very well known to you. If you know that, then only you can apply, otherwise you can't apply. Okay. Now coming on to the last example of today's class, this is another good problem which you might see. All the questions are of different types. I'm just doing the types for you. So fourth example, express the function defined by the following graph in terms of the unit step function and find their Laplace transform. So one graph is given. From the graph you have to express the function in terms of the unit step function and then find its Laplace transform. Clear? So what is the graph? This is the graph given. You see? This is the graph given here. You can clearly see it's a graph. So it's 0 to 1, then 1 to 2, then 2 to 3, then t greater than or equal to 3, right? It's 0. So from the graph, it is very easy to see that we can write the function immediately. We can write the function immediately from the graph. That we'll do first. So from the graph we have, we are writing the function here, ft equal to 0. You can see for I just go back to the graph once again to make things clear. Ft will be equal to 0. You see ft is 0 for t less than 1, okay, that is from 0 to 1. T1 is like from 0 to 1, ft is 0. So I have written ft equal to 0. Now ft is equal to t minus 1 from 1 to 2, right? 1 to 2. Why 1 to 2? Because you see it is clearly a linear function, straight line. Okay, so it's t minus 1. So from 1 to 2, this part of the graph. Okay, this part of the graph is t minus 1. Then we get this part of the graph, that is from 2 to 3. It is 3 minus t, isn't it? It's 3 minus t from 2 to 3. And then from t greater than or equal to 3, it is 0 once again. So you see, basically this is the function we are getting. So t minus 1 from 1 to 2, 3 minus t for 2 to 3, and 0 for t greater than or equal to 3. So we have written the function first. That is very important. From the graph, you write the function first. Once you've written the function first, you now have to do the second step. That is, you have to write this in the form of a unit step function. So you have to write that then in the form of unit step function. Once you are able to write them in the form of unit step function, then only you can take the Laplace transform on both sides and get the answer. So let's write this function in the form of a unit step function. So how we write it? Same way. So we write ft equal to t minus 1, the function, into, because f1t is 0, so I don't have to write f1t is 0. So your this is your f2t, t minus 1, into u1t minus u2t, plus 3 minus t into u2t minus u3t. Okay, right? And your f4t is 0, so don't write that. So is equal to, so now this becomes t minus 1 into u1t, just simplifying it. We take the coefficient of u2t and we find that it is 4 minus 2t into u2t. Okay, then minus 3 minus t into u3t. That's what we get. We are just simplifying it. After writing this in the form of this form, we are just simplifying this. Okay, from the theorem we are writing this in this form, as we all know. So we get this, right? And now we are getting t minus 1 into u1t minus 2 into, take 2 common, so we get t minus 2 into u2t plus t minus 3 into u3t. That's what we get. Once we get this, now we take Laplace transform both sides. So we take Laplace transform both sides. So L of ft becomes now L of t minus 1 into u1t. So if we apply the shifting property, so we get e to the power minus s, a being 1, so it is e to the power minus s, into the Laplace transform of u1t, which is 1 by s square, because it is a linear function of t, L of t. So L of t we all know, it is, what is L of t to the power n? L of t to the power n is n factorial by s to the power n plus 1. So L of t to the power 1 will be 1 factorial by s to the power 1 plus 1, which is 1 by s square. So that's why we get 1 by s square here. Then minus 2 into e to the power minus s, a being 2, so minus twice s, into ut again is the Laplace transform of a t, which is 1 by s square, and plus e to the power minus 3s, a being 3 here, into Laplace transform of t, which is 1 by s square. So we get this e to the power minus s into 1 by s square minus 2 e to the power minus twice s into 1 by s square plus e to the power minus 3s into 1 by s square. So finally, if you can take 1 by s square into e to the power minus s common, you get 1 minus twice e to the power minus s plus e to the power minus twice s. And then you can write this first bracket term as 1 minus e to the power minus s whole square, right? We can write that because we can write that this is just a minus b whole square. So we do that. Now from this, I take e to the power minus s common. If we take e to the power minus s common, you should get e to the power s by 2 minus e to the power minus s by 2 whole square, because whole square is there, so it will be s by 2. If we take minus s common, it will be actually get s by 2. Now e to the power s by 2 minus e to the power minus s by 2 can be written as 2 sine hyperbolic s by 2. So I replace e to the power s by 2 minus e to the power minus s by 2 by 2 sine hyperbolic s by 2. Since it's square, so it becomes 4 sine hyperbolic s square by 2. Sine hyperbolic square s by 2 divided by s square into e to the power twice s. So that is the final answer of this particular question. 4 sine hyperbolic square s by 2 by s square into e to the power 2s. So I hope you have understood all these 4 problems in today's class. All the 4 problems are of different types, and these are the types of questions you will get in the semester exam. So you have to thoroughly practice these types of problems from a standard book. Okay, so with that I come to the end of today's class. Hope you have enjoyed it. So we'll come back again on the next week on discussing on more topics on Laplace transform. Thank you very much.